Hey everybody, it's Dr. Wood, and today we're going to be going over some more epidemiology and biostatistics. And we're going to be going over lecture 7, where we're going to be talking about fitting models to data. What exactly does that mean? Here's some objectives we'll cover. I'll let you kind of read those on your own. Getting into simple linear regressions. This is going to be a continuation of the correlation example we were talking about last time, where we were looking at the lipid content of cell membranes versus insulin sensitivity and how that had some effect, how you can correlate one versus the other. And so when we do a simple linear regression, basically what we're doing is by graphing out those two variables there, we're trying to get a best fit line. If you recall, last time we were talking about R and R squared values and things like that. And, we just saw a correlation between those. We couldn't necessarily say that one was causing the other. But you're going to see here that when we do one of these linear regressions to the data, we're going to try to find the most likely values for that parameter that define that model. The point here is that instead of just looking at a pure correlation in some data we have here, how can we develop a model and then apply that to other patients? So that way, if I did know what their lipid content was, I could then determine what their insulin sensitivity might be, right? So what are some goals here? So when we're looking at the insulin resistance data, we remember that we had two variables, and we had the insulin sensitivity and the fraction of the fatty acid there. And so what they were proposing was a model that they were saying the insulin sensitivity is a linear function of that percent of fatty acids, and that as the fatty acid content goes up, so does the insulin sensitivity. And I'll show you the data here in just a second, but it's going to look like we saw in the last lecture. Basically, though, we just have the simple equation for a line here. If you guys remember, y equals mx plus b, or here's just rearranged a little bit. But basically, our insulin sensitivity, which is going to be on the y-axis, is going to be equal to the intercept plus the slope of the line times the C20 to 22% content. So by knowing what this variable is and knowing what the slope and the intercept is, we'll be able to determine what the insulin sensitivity is in that case here. Okay. Now again, we're going to find that the model will not directly account for random variation, and it should be a standard assumption here that we're pulling our data from a randomly selected group of individuals and a pretty representative bit of the population there. They should be following a Gaussian distribution. So that will be one of the assumptions we're making for this exercise. So our goal, though, is to try to find the values for the intercept and slope that are most likely to be correct and try to quantify that imprecision with the confidence intervals, right? So we're taking this data that we have, we're developing a model for it, and that model is going to be illustrated by that equation for the line we saw in the last slide. And then we're going to try to apply that out to other individuals within the population. And so because there's going to be some inherent variability there, you're going to find that we'll get a best fit line, but there's also going to be some confidence intervals there to help us account for the fact there's going to be some random variation. We can't know what that line will be exactly for all individuals. And so we're going to look at this in a graphical sort of means, and I'll show you what that looks like in a moment. But again, this is the line that best predicts y from x. So for a given value of x, what is the most likely value for y? And this is what the model is trying to tell us here. So looking at this graph here, you can see the percent fatty acid content here on the x-axis and the insulin sensitivity on the y-axis. And basically what we're trying to look at is looking at all the data points here. We're trying to figure out what this best fit line is, such that if I know what a patient's fatty acid content is, I could basically predict what the y-axis is going to be, or the insulin sensitivity in this case here, right? And so just to give you a different example of what that looks like. So if it came up and it was 21% of these fatty acids, I can basically just kind of go straight up if I could draw a straight line, and then draw straight over here, and it would be up roughly 300 for their insulin sensitivity, right? And again, you're going to find that this is not an exact line. You're going to find these confidence intervals here, which is accounting for some of that variability in the data itself. Because as you know, this R squared value was not 1 here because not all the data points lined up directly on that line. So just a few points to make here on this chart. Basically, when we're looking at the best fit values, that slope is determining how steep or shallow that line is going to be, and determining how big of a difference y changes in response to a change in x there. So that's just one thing to note. Notice here the y-intercept when x equals 0. There's probably not going to be a biological example of where x would equal 0 in this case. But what presumably with the y-intercept be here. Notice this is a negative number, which doesn't really make sense. I don't know if you can have a negative insulin sensitivity, or maybe you are, I don't know, expelling glucose from your cells or something like that crazy. But these don't always have to be physiologically relevant. It just is a point to note in terms of making our model, essentially. Again, you're going to find that there's going to be 95% confidence intervals here. So with the slope, you can see it ranges anywhere between 16.75 to 57.67. Again, the true slope of that line could be anywhere in this range here when applied out to the general population, and of that, the authors would be 95% sure. Remember, R squared value is really good, and again, it tells us kind of how well all the data points fit to that line. And 0.59 is not great, but it could always be a little better for sure. But better than having a line of 0, in which case there would be no, just be a horizontal line at that point. There'd be no way you could predict one value from another. Okay, so let's look at the results of this linear regression. So we see here, again, the slope is 37.21 plus or minus 9.269. Again, there's going to be some inherent variability there, but this is basically the slope that we came up with. So as you increase the x value, the C 20 to 22 percentage by 1, you should see an increase in insulin sensitivity of 37.2 milligrams per meter square, right? And again, you're going to see that confidence interval will range there. It's fairly wide, but it doesn't include 0. So in this case here, we're going to look at another example of why the point of 0 is going to be our level for significance. But because it does not include 0, you're going to find that there is a degree of relationship here. There is a statistically significant association between this confidence interval that we developed here, the slope of the line, and actually being applied to the general population. Now remember, what we said is that if the R squared was 0, that slope was 0, basically you couldn't interpret any sort of data there because X would not predict Y. And so as long as the confidence interval does not include 0, then you can say that, okay, there is at least some evidence that we have a relationship here between the two and that you can predict Y from X. As I mentioned, the y-intercept is not really so important here, even though it is negative. Again, this is just helping us to develop the model itself. It does not have to be biologically plausible. Looking at the graphical results, again, the graph will show that best fit regression line, and then you end up having two lines outside of that to basically show you what the 95% confidence bands look like. Again, that shaded area is going to be that where the true line could actually lie in any of those points there. And even though only a few of the data points actually fit into the confidence bands, it's not that big of a deal because that's just how the data ended up scattering out. But again, if you would apply this to, say, a different data set, you may be able to get more of the points in there, less of the points. It just really depends on the information. But again, looking at this, you may find that the actual slope of that line could be anywhere within the shaded area here. So it could look something like this. It could look something like this. Point being, it was going to be somewhere in that shaded area, and of that, you were 95% sure because that's what the confidence intervals are telling you. As I mentioned, the R squared value of 0.59 basically tells me that 59% of all the variance in the insulin sensitivity can be accounted for by that linear regression. Now, note there's still a significant amount of variability that's not being explained here, roughly 41%. And so because of that, there's probably other factors that are playing a role here that the researchers have just not taken into account. Could be errors in the measurement, could be biological variation, there could be other factors that we're not really accounting for here. And again, when you're looking at the p-value, it was 0.0021, which makes sense because the confidence intervals did not include 0. But to look at it another way, our null hypothesis when developing a model like this would be that there is no linear relationship between that fatty acid content and the insulin sensitivity. And in that case, the slope would basically be 0 because there's no prediction that can happen there. However, we can say that because the confidence intervals do not include 0, that would give us a very small p-value. And so we do reject that null hypothesis and say, no, there is a relationship here and that you can predict insulin sensitivity from that fatty acid content. Now, correlations and linear regressions are related. Note here that with the null hypothesis for a correlation, there's no... Basically, it just says that there's no correlation between X and Y, that the two variables there, they have no relationship to one another. When you're dealing with a linear regression, know that the null hypothesis is just going to be a horizontal line, right? Basically, these two null hypotheses are essentially equivalent. If you were to have a correlation with the null hypothesis being true, that would be a flat line. There would be no relationship between the two there. And again, p-values for both of these sets are going to be identical when you're actually able to calculate these out. what are some assumptions we're going to have here when doing linear regressions? Well, we're assuming that the model is correct. However, keep in mind not everything is linear, right? So you may find that while a linear regression will give you a line that will extend out to any value you want, note that that may not always hold up. As you get to further and further values away from the data you're actually looking at, you may find that relationship does not stay linear, right? And so you have to do more complicated modeling in order to do that. Again, for our purposes, though, we'll just work with this assumption. However, you may find that some researchers may violate this, and that would make your data less robust. It would not really withstand much more scrutiny than that, and it would potentially be making a type 1 error. Another assumption we're going to be making is that the scatter of the data around the line is going to be Gaussian. Again, this is just our assumption that we're having randomly selected data. It's normally distributed, all of that, and that variability should be the same everywhere. We're also noting that the data point should be independent, such that you're not measuring the same person twice. There's no siblings in the study, anything like that. Also, the X and Y values are not intertwined. So it should not be that because you directly change Y, that X is going to change necessarily. What we're trying to see is that based on the value of X, what is the predicted Y? And if the two are intertwined, then you can't really make that assumption anymore. And then also your X value should be known pretty precisely. You would not want to have imprecise data because then obviously that messes with the model. So to compare linear regressions with correlations, again, with the correlation, it's just quantifying the degree that two variables are related. It doesn't necessarily have to fit a line, so to speak, but it will tell you basically that when one variable changes, the other one tends to change as well. You don't really have to think about cause and effect here, and in this case, it doesn't really matter which values X or Y, because you're just looking to see, do they kind of change in the same direction, or do they kind of have some relationship to one another, whether it's a proportional relationship, whether it's inversely proportional, whatever the case may be here. With regression, though, this is where we're starting to wonder about predictions. And so you really want to make sure that you have your X's and Y's straight, because in a linear regression, the Y value is what you're trying to predict. The X value is what you're going to know in those sort of situations there. This is where you're thinking much more about cause and effect than you would be if you're just doing a simple correlation there. So some other lingo you might hear when dealing with regressions is that linear just means that we're looking at a very simple sort of relationship between the two. Obviously, you can have nonlinear relationships, but this is what we're going to be working with for our purposes today. Most of the ones you're going to find in the medical literature tend to be linear regressions. The more important thing to note is it a simple versus a multiple linear regression. When dealing with a simple linear regression, there's only one X variable here, and in our example, we are looking at the fatty acid content, whereas with a multiple linear regression, this is where we're using two or more X variables, and obviously this is where things tend to get a little more complicated. So let's look at how we're going to be introducing models. So some of your goals when trying to develop a model is to try to find the best fit values from a data set that define that model, right? So just like we mentioned with the linear regression, you're taking an actual data set where you collected information and then developing a model off of that, right? That's going to be that mathematical set of equations that are going to be able to better represent or describe either a physical, chemical, or some sort of biological state or process. And basically, we can then take that by taking data and fitting a model to it, we can then take that model and basically simulate what data we would expect to find from there, such that once I have that model, I can then say, well, based off of a patient having a fatty acid content of X value, I can pretty well assume that their insulin sensitivity is going to be Y, right? So again, this is what we're taking. And imagine as well, like when you're looking at equations like, say, how to determine creatinine clearance, right? The Cockcroft-Gault equation. That was a model that was based off of actual patient data they did many, many decades ago. And so now we take that model and then we apply it to our other patients, such that once we know their age and their weight and their serum creatinine, we can then predict what their creatinine clearance is, right? So that's kind of a good example I like to go to in terms of illustrating that concept. So again, when you're developing a model, this is where you're using your regressions that fits that model to the data, right? You're trying to find the best equation that's going to be able to accurately represent that data, especially when you apply it out to other individuals, right? So when you're developing that equation, it's adjusting the values of the parameters in the model, and it will then be able to make predictions of the model as close as possible to that actual data, right? So if I were to run that model and then compare it to the data that you actually collected, it should come up with very similar values in those cases there. Otherwise, it's not a very good model. And so remember that we're seeing that regressions do not fit data to the model, but rather it's the model that gets molded around the data. And so if you kind of think about the data as being your feet and the models being shoes, you try to find shoes that fit your feet. You can't change the size of your feet, right? So that's kind of what we're talking about when getting these models here. Now let's look to see how we can compare models. So one of the things you'll find when looking at different types of models is that the more parameters they have and the more things they take into account, they are always going to fit the sample data a little bit better, but it may not really reflect accurately what's going on with your population here. And so looking into the number of variables you have, you can see that a model with too few variables really just doesn't fit the sample data that well, unless your predictions when applied to the larger population aren't going to be that accurate. On the other hand, though, if you have too many parameters, it may fit the sample data really well, but you may find that the confidence intervals are so wide as it's going to be kind of useless when you end up applying it to the larger population there. So you kind of want to fit the model to the data, but you don't want to overfit it and make it too tight. You got to have a little bit of wiggle room in there such that you can account for some of that biological variation that happens in the normal population. Again, when you're comparing this straight line versus the best fit line here, the linear regression, you see that there's much better scatter of the points around the best fit line than it is just that straight line. And again, more of that variability is being explained here than it would be with just a straight line, which is why we can reject that null hypothesis. So next, let's talk about a few different types of regression you might run into when reviewing the medical literature. So first thing is going to be multivariable regression. And so in these cases, when you're running a laboratory experiment, you basically control all of the variables, especially the independent variables, the ones that the experimenters are changing here. And so in the experiment, you can change one variable, measure another, and then analyze that data with the help of sort of standard statistical tests there. In some of these cases, though, when you're running these experiments, you have to analyze how one variable is influenced by several variables, right? So instead of just changing one thing and seeing how the variable changes, here we might have to see how the influence of multiple variables plays a role in determining or predicting a particular value. So in these type of experiments where we're looking at a number of different variables and trying to figure out how they may affect our outcomes, you can see here this is where our multiple variable methods come into play here. And they're very widely used. You'll see them all the time in the medical literature. We're just going to kind of introduce the basic concepts here. But when we do a multiple regression, we're going to be using these methods here for a couple of different purposes. One, they're going to be able to assess the impact of one variable while adjusting for others. When I say adjusting for, I mean kind of controlling for and kind of saying, well, with all these other things being equal, what's the impact of this one particular variable? We can then create an equation making for those useful predictions, right? This is how we develop a model like the Cockcroft-Gault equation. And then we'll be able to kind of scientifically understand how various variables may have an impact on a particular outcome. When we're talking about multiple regressions here, again, there's several different methods that can kind of fall under the term multiple, and we'll talk about a few of the more common ones here. With variables, though, remember it's important to define what our independent versus dependent variables are. The value that we're trying to predict as an outcome is going to be our dependent variable. This is going to be the y value. When we have one or more predictors, we're going to call those independent variables. So you can have multiple independent variables. Typically, though, you're looking for one dependent variable, right? So multiple independents because the researchers are setting those, and then one dependent typically. Now, you may hear the term multivariate used kind of inconsistently in mixing that up with multivariable. Sometimes it's referring to a method that is comparing several outcomes at once. This is correct and not something we're going to be doing for our purposes, kind of outside of our scope. And then what we're really going to be looking at is when we're using one outcome and several independent variables. That's the multivariable one. Multivariate means you're looking at several outcomes. So getting into multiple linear regressions, again, this is finding that linear equation that best predicts y from multiple independent variables, right? So instead of just a simple linear regression, this is a multiple linear regression. And so there's a study here back in 92, they're looking at lead account, or they're looking at does lead account for decreased kidney function with age. Okay, so they're looking at a couple different things here. Does lead account for the decreased kidney function with age? So they're trying to look for a couple of different things here. And so they're looking at the relationship between lead exposure and kidney function, because one, we do know that lead decreases kidney function. We also know that kidney function decreases with age. And we also know that most people tend to accumulate at least small amounts of lead as they get older. It's just one of those natural things you pick up just from the environment in a lot of cases there. So they want to know whether accumulation of lead could explain some of that decrease in kidney function with aging, or is it maybe just related all to aging by itself? So again, we have a couple different variables we're looking at, with ultimately the outcome being kidney function. So they had 965 men. They also studied women, but we're only going to look at this particular data set here. And they measured the serum lead concentrations and creatinine clearance. And then what they tended to find was that subjects with more lead tend to have lower creatinine clearances. And then, although this is not really as useful a finding, because we also know that lead increases with age as well. So again, we are trying to figure out, well, how much of this is just due to the lead content versus how much of this due to just age alone. And we're introducing a term now called confounding, or confounders. And in this case here, age tends to be the confounder because we know that it has an effect on creatinine clearance, but we need to determine how that's playing a role versus just the lead itself, or maybe there's a relationship between the two here. And so again, a confounder is any sort of bit of extraneous variable that correlates either positively or negatively with both our dependent and our independent variable. And so the thing you can do with this is you can control for the confounder, and that way when you control for it, you're basically taking its influence out of the data, and that way you can better look at the things you're actually interested in this case here being creatinine clearance and lead content. So to adjust for the confounders, they end up using a multiple regression that adjusts both for the age of the patients and for other factors here. And so you're going to find that the X variable is going to be the log of the lead concentration. The Y variable is going to be our dependent, and that's going to be our creatinine clearance. And then the model then predicts its value from the baseline value plus the effects of a few other different independent variables. And then we're going to see that each get multiplied by a certain parameter. This will make more sense when we look at the outcome data. So when you're actually looking at the different variables they were looking at, the different independent variables they were accounting for, they're going to be seeing that the log of the serum lead concentration was one they're mainly interested in. They're looking at age, looking at the body mass of the patient, the GGT, which is a marker they were looking at, and the use of diuretics. Okay, so these are kind of the big things they were focusing on in terms of the independent variables that they were looking to control for, with their outcome mainly being this creatinine clearance. And again, this is going to be the y-axis. All these other ones would be accounted for on the x-axis. Note when you're looking at the independent variables, the units don't really matter. You can kind of use anything you want. So as an example, with diuretics, it's just mainly a yes or no, or 0 or 1, versus body masses in kilograms per square meter, ages in years. This doesn't really matter here. Your X or your independent variables can always be different units. So the goals when we're doing these regressions here is with a multiple regression, we're trying to fit that model to the data that we have, so those 900 some odd men that we're going to be looking at, and find the values for the coefficients that make the model come as close as possible to predicting the actual data here. And again, we're trying to find that best fit value for each parameter along with a confidence interval. And so we're going to find that one p-value gets reported for each of the independent variables, and to see like, okay, well, does this one actually have a best fit line over the null hypothesis for each of those independent parameters? And we'll see what that looks like when we get to the actual data itself. Remember, when our null hypothesis in these sort of cases here is that the given parameter, the given independent variable, has no information in terms of predicting what the y value is going to be there. And again, that best fit line for that parameter would end up being 0 if it was not significant, or if that was the null hypothesis was true. So how do we interpret these coefficients here? You're going to be looking at the multiple linear regression models to distinguish those x variables between the ones that I really care about and the ones I'm adjusting for. When you are adjusting for different independent variables at a time, those are called covariates when you're looking at one particular variable. Okay, so again, when we're trying to look at the actual data, it's important to make this distinction. The investigator's goal, though, was to see that when you adjusted for these other variables, is there a substantial relationship between that logarithm of the lead concentration and creatinine clearance? So by adjusting for things like body mass, adjusting for diuretic use, adjusting for all these factors, was there still a linear relationship between lead concentration and creatinine clearance? So the end of finding is that the best fit line for the logarithm of the lead content was negative 9.5 mLs per minute, meaning that as you had the value of lead go up by 1 unit, you're going to find that the creatinine clearance dropped by 9.5 mLs per minute. And when they adjusted for the other variables and saying, okay, let's take out the effect of age, let's take out the effect of body mass, etc., this is what they end up coming up with. And notice here the confidence interval is negative 13.9 to negative 5.1. If this included 0, you would basically not be able to reject the null hypothesis and say, okay, well, I can't really predict creatinine clearance just from the lead content. I know that there's not a good linear relationship between the two there. Okay, and so what you end up finding was that 10-fold increase in lead concentrations would end up reducing renal function by about 10%. He said confidence interval ended up going from about 1 to 20% when they did the data. And so you can see here, looking at creatinine clearance on the y-axis and then looking at the change in lead concentration, that the relationship here is linear, but you notice the confidence intervals are changing pretty widely there. They get pretty wide towards the end, which makes sense because you're seeing the logarithmic increases in the x value here. But again, notice here that the confidence interval does not include 0, and because of that, we can say that, okay, let's reject the null hypothesis and say that, yeah, knowing the lead concentration, we can predict what the change in creatinine clearance is going to be because we've accounted for the other variables here, and we still see that there's a significant relationship. Now, it's okay that our confidence intervals are negative because there's an inverse relationship between the two factors there. As lead goes up, creatinine clearance goes down, right? So those negative values are perfectly reasonable, but because the confidence intervals do not include 0, you can reject that null hypothesis here, okay? And even though they don't specify the actual p-value, we can assume it's less than 0.05 because we know how to interpret the confidence intervals. So the next question to ask is, well, how well does the model actually fit the data? When you actually look at the r-squared value of this, you end up seeing it's only 0.27, meaning that only 27% of the variability in creatinine clearance was explained by the lead content. It means that the other variability we saw was random. And so because of that, there's no real way to say, well, let's have one best fit line because there's just too many independent variables there. But in this case, we can say that 27% of the variability is due to lead, and that the other variability is probably due to the other independent variables that we're running into. And again, actually looking at the data here, if you're actually looking at actual creatinine clearance versus predicted, you can see here that the r-squared value only being 0.27, there's a lot of scatter around here, and even though that is significant, there's still a lot of variability that you can't really account for because of this. Now, again, we're trying to find these correlations. It doesn't imply causation. It doesn't say specifically that lead causes renal function to drop. They're just showing that that relationship exists there. As lead increases, we do see that there is a drop in creatinine clearance. And so because these are observational studies, you cannot determine cause and effect here, right? The best way to do this would be by experimentation, right? By exposing people, one group to lead and the other group to no lead, and seeing how their creatinine clearance changes, right? Obviously, that would be a very ethical experiment, but there are other ways to get around that as well. We'll talk more about study designs a little bit later on in the class. So let's look at another type of regression here. This is going to be a logistic regression. And this is where we're going to be looking at two possible outcomes. So instead of having just one outcome variable, we're going to be looking at two of them here. And so there's a study done back in 2008 where they're trying to get a model to predict the prevalence of obesity in Iranian women. And so their outcome, obesity, was considered binary, right? So two possible outcomes, either yes or no. And so what they ended up doing was creating a model that predicted the prevalence of obesity as a function of different demographic variables that could have an influence here. So it could be where they lived, it could be if they're smokers, it could be a couple different things, as we will see. So notice here they're using logarithms, and this is because when you develop odds ratios, they typically end up being sort of asymmetrical, but by using the log of the odds ratio, they become symmetrical at that point. And I'll talk about what that means in just a moment. So when doing this study, they found they had 8 independent variables they were looking at. So the model ended up having 8 odds ratios as their outcomes. And so basically the odds ratio is answering the question is that for a particular value, if it was increased by 1, keeping all other factors the same, how much would the logarithm of the odds ratio be expected to increase? Okay, so again, you're still controlling for the other factors here, but if this one value changed, how would the odds ratio actually change? So when you're looking at the odds ratios that this develops, you'll see that if it's pretty close to 1, that means that having that independent variable present really doesn't have much impact on the outcome. So if it's 1, essentially, it means that your odds really haven't changed whether you have that independent variable present or not. If it's much higher than 1, then it usually means that having that independent variable present means that you have an increased likelihood of the outcome occurring, which in this case is obesity. If it's much less than 1, then you tend to find that increasing the independent variables associated with the decreased likelihood of the event actually occurring. Now here are the different odds ratios we've come up with for each of the values here, and you can notice here we have independent odds ratios are being reported out for each of these. Note here that if you have a confidence interval that crosses 1, that means that that is not statistically significant. That means that the p-value is probably greater than 0.05, and thus it would mean that there's no relationship here between the independent variable and then the outcome. And so in this case here, you can find that each of these is actually statistically significant. This is easier to attain when you have very large sample sizes. However, some of these are very close to not being significant. So for instance here, this one is 0.98. You see it ranges here between 0.968 to 0.993. This has very little input on the actual incidence of or prevalence of obesity in the population here, right? versus looking at something like they're urban, like whether they live in an urban environment or not. You can see here that this has much higher odds of a patient being obese if they live in an urban environment. So if this is present, then it means their odds are twice as high of them being obese. However, is there anything that's protective? We can look here to see if smoking appears to be protective, even though it has a pretty wide confidence interval, close to 1, but doesn't cross it. And you can see here that this tended to be smoking was associated with lower prevalence of obesity. Okay, and again, I'll go over more details on these, but this is kind of the preliminary sort of read on these outcomes. So again, when you do a logistic regression, it's going to compute an odds ratio for each independent variable along with that confidence interval. As I mentioned, if they live in the city, there's a corresponding odds ratio of 2.13, meaning their odds are twice as high. They're going to be obese if they live in an urban environment. Okay, doesn't mean everyone's going to be obese. It just means their odds are that much higher. And so, just like I said here, you can see that when you report out on one of these outcomes, you're keeping all the other independent variables. So you're making sure you're accounting for that smoking is not influencing it, that socioeconomic status isn't influencing it. You're just looking at whether or not they live in an urban environment or not. And again, here you see the confidence interval ranges between 1.9 to 2.4. It does not include 1, so we can reject that null hypothesis and say that yes, there is a relationship here. The people who live in an urban environment have a higher odds of being obese. So do you always have to decide which variables is going to be the outcome dependent variable and the predictors is the independent as the time of data collection? Not necessarily, but in some cases it may not really be clear until you start doing the data analysis as terms of what you want the outcomes to be versus the actual independent variables there. However, you got to be careful as to not overfit the data to kind of find as many variables as possible to predict your outcome because then it may not really be generalizable to a greater population. Okay. Does it make sense to compare the value of one best fit parameter with another? Not really, because the units of each parameter tend to be different, so there can't really be a direct sort of comparison there. Just like you're looking at logarithm of the lead concentration versus, say, the age of the patient. That's not really a good way to compare those, and there are ways to do it, but it's not going to be in the scope of this course. And then do all the independent variables have to be expressed in the same units? Nope, as I mentioned, they can be totally different units, and there's no problem with that. So that's it for this section. If you have any questions, please let me know, and I'll see you next time. Thanks a lot.